same slope as this one. And then I could have tried to find the y-intercept up here, which would have been 8. But that's how you do it systematically. All right, so this has the equation y equals negative 3x plus 8. And now what I'll do is the same exact thing I did just a second ago. I'm going to rewrite that equation of that line segment. Y equals negative 3x plus 8. And I'm going to replace y with 1/4 v minus 3u. I'm going to replace the other side, negative 3x is 1/4 u plus v, and then plus 8. Okay, so I will multiply everything again by 4, so that'll kill off this one and this one, but this will also be hit by 4. So I'm going to get v minus 3u equals, this is gone, distribute, negative 3u minus 3v, but this time I have plus 4 times 8, which is 32. Notice again that the 3u's cancel, the negative 3u's will go away. Let's move this 3v over, so you get 4v equals 32, and then v must be 8. So now I come back over here and I say, all right, where is v equals 8? So let's say that that's 8 units right there. V equals 8 is another horizontal line. So I've taken these lines that have some slope to them, right? And under this transformation, I've flattened them out. And that's creating what looks like is going to be a rectangle. All right, now I need to find 2 more line segments, the equations of 2 more line segments. Let's do, I'm running out of colors here. I'll do this one in green. Let's do this one right here. Okay, so the slope on this one, I went, let's see, to get to this point, I have to go up 1, 2, and over 1, 2. So that has a slope of 1, y equals 1x. And then where's the y-intercept? Well, if I go up 1 over 1, up 1 over 1, if the slope is 1, then to get to the y-intercept, I go back 1, down 1, which would put me right here. It's 1, 2, 3, 4. So negative 4 is the equation of this little line segment. And then I'll come over here and do the same thing. So y equals x minus 4, and y is 1/4 v minus 3u equals x, which is 1/4 u plus v, then minus 4. Multiply everything by 4. V minus 3u equals u plus v. And I multiplied that by 4, minus 16. And this time, notice that if I subtract v on both sides, it goes away. And then I'll move this u over. I get negative 4u equals negative 16. So u must be 4. So u is 4. How are we doing on time there? Yeah, we're okay. U is 4. So this time over here, u is 4. I'll use blue. U is 4 is about right here. And it's a vertical line. U is 4. And one more line segment to go, and I'll have the new region. So this one right here, the slope of that is also going to be 1. And the y-intercept, I kind of drew it wrong. It hits right through there. So it's up 1 over 1. That should be at 4. So plus 4 here. So when we come over here, the only difference is that this is going to become plus 4, plus 4, plus 16, plus 16. Divide through by negative 4, you get negative 4. So instead of u is positive 4, I get u is negative 4. So check out that region over there. I've taken, this wasn't real complicated, but if we were going to try and integrate over this region, we'd have to break it up into type 1 and then do several different integrals or different regions. That is a really nice region to integrate. So what I've done at this point is I know my new double integral, my restrictions on u between -4 and +4, my restrictions on v are between two constants also, 0 and 8. So this is going to be a really nice integral as far as the limits of integration. But I need to now go and transfer this double integral into the new double integral. And when I do that, all my x's have to be replaced with the function, all my y's have to be replaced with the function for y, and I need the Jacobian in there. So let me go after the Jacobian right now. Okay. So remember, what I'm doing is I'm taking this, turning it into a new double integral over some region. I'm going to call that S, and I'm going to have my original function in here 4 with x plugged in, which is 1/4 u plus v, and then plus 8 times y, which is 1/4 v minus 3u, and then whatever all that is, times the absolute value of the Jacobian, which is this, and then d, in this case it won't matter, du dv or dv du won't matter because those are both variables are stuck between constants, so order of integration doesn't matter. So I'm just going to go try and get this now. So what is my Jacobian? Well, the Jacobian, partial xy, partial uv, is equal to the determinant of partial x with respect to u, partial x with respect to v, partial y with respect to u, partial y with respect to v, which we said just a second ago was this times this minus this times this. So partial x with respect to u times partial y with respect to v minus partial x with respect to v times partial y with respect to u. All right, so I need to take some partial derivatives now. What is the partial of x with respect to u? So here's my, I'll leave that there. Here's my x. Let me just distribute that 1/4 through. 1/4 u plus 1/4 v. Y is equal to 1/4 v minus 3/4 u. All right, so what is the partial of x with respect to u? So this is a constant. Derivative of this with respect to u is 1/4. Partial of y with respect to v is partial of this with respect to v, which again is 1/4. Minus the partial of x with respect to v, which is, let's see, 1/4. And then times the partial of y with respect to u, which is here, derivative of that is -3/4. All right, let's clean this up. 1/4 and 1/4 is 1/16. Minus over here, -3/16. Which the minus minus becomes plus, so you have 4/16, which is 1/4. So this becomes, I think I'm ready to write this out. This double integral becomes double integral. I'll put the limits of integration on in a second. I already switched my x's and y's over, so let's kill that off. That's just u plus v. And then multiply that through to here, that's a 2. Then pass that through, you get 2v minus 6u plus 2v minus 6u. And then I need the absolute value of the Jacobian. And this is the Jacobian 1/4. And then your du dv or dv du doesn't matter. I'll do du dv. The restrictions on u were between -4 and 4, and the restrictions on v were from 0 to 8. So my Jacobian on this one, the Jacobian determinant, the magnitude of it, the absolute value of it is just 1/4. That turned out to be a constant. It's not always going to be a constant. So I could pull that 1/4 out, which I'll do. 1/4 integral 0 to 8, integral -4 to 4. let's see, u's I have negative 5u, v's I have 3v. I'm going with respect to u, then v. So let's take the antiderivative of the inside with respect to u. So you're going to get negative 5 halves u squared, and then the antiderivative of this with respect to u is plus 3vu. Evaluating from u equals negative 4 to u equals positive 4. Then I'll integrate with respect to v. All right, so if we plug in If we plug in 4 for u, we get 16 here. Divided by 2 is 8. 8 times negative 5, you get negative 40. If I plug in 4 here, I get 12v plus 12v. Then minus, now plug in negative 4. If I plug in negative 4 here, that's squared, I still get 16, then half of that is 8, and then so I still get negative 40 there. And then here, negative 4, I get negative 12v. And then dv. And I believe this negative 40 cancels out with that negative. Negative is positive, so that negative 40 is going to be gone. This is going to become plus 12v. I already had a 12v, so I should be looking at this. 1/4 integral 0 to 8 of 24v dv. Go ahead and pull the 24 out. Just make that a 6 out here. Why not, right? The antiderivative of v is going to be 1/2 v squared, but then times 6. So 3v squared, evaluated from v equals 0 to 8. And 8 goes in there, 64. 64 times 3, 180, 192. And then 0 goes in here, you get 0. So 192 is the value of that double integral. That's a lot of work, okay? I understand that. I agree that that's a lot of work. This is more just to show you how it works rather than trying to convince you that this was the more efficient way for this problem. All right? Maybe this problem we should have just left it in Cartesian. Maybe it would have worked a little better or a little faster maybe. All right? But again, it's just the method that I'm looking at here. Okay, so I'm going to do another one here. Let's do the double integral over d of e to the x plus y over x minus y with respect to area, where d is this trapezoid given to you with these points as vertices. 1, 0, 2, 0, 0, negative 2, and 0, negative 1. So your region looks like this. That's D. Okay, so what we're trying to do is do this double integral. In this problem, no transformation is given. So let's see why we wouldn't want to do this double integral. Let's say we were able to write this as a type 1 or a type 2 or some combination of those. Integrating this with respect to y or with respect to x would be very challenging. So it doesn't look like I want to do that. So I need to come up with a transformation. Well, it's difficult in this sense to figure out what you need that to be. Like you need to write x as a function of of u and v, and y as a function of u and v. But if I just kind of make a wild kind of educated guess here, what if I let u be x plus y and v be x minus y? If I do this, then this integral becomes e to the u over v, right? It would become e to the u over v. And if I have to integrate that with respect to u, that would be relatively easy to do. And with respect to v, it might be a little harder, but I know I can do that with respect to u. I could not do that when both variables appeared in the top and bottom. So that might be a good first shot at this. But remember, I need to write x as a function of u and v, and I need to write y as a function of u and v. Right now, I've written u as a function of x and y, and v as a function of x and y. So let me switch these over to look like this first. So what I'm going to do, I can take u equals x plus y. I can take this equation right here and solve it for x. So this is x is equal to v plus y, right? So if I rewrite this, this is u is equal to v plus y, right? That's what I get there. So u is equal to v plus 2y. But, well, yeah, I guess I could do it that way. You know, I still need y. Well, if I solve this for y, I have y as a function of u and v. There we go. That's what I can do. So u minus v, if I subtract, I get 2y. And then multiplying both sides by 1/2, I get y is equal to 1/2 u minus v. So notice y is now a function of u and v. Then I'm going to figure out what x is. So let's go up here to this equation we had for x. X is v plus y, but y we just said was that 1/2 u minus v. Let's distribute the 1/2 through 1/2 u minus 1/2 v. So x is equal to v, and then, take a v and subtract a half v, I get another half v. Half v plus half u. So x is equal to 1/2 u plus v. So there we go. We've got our two x and y equations, both in terms of u and v. So this was kind of my guess as to what I was going to replace these with, and then I was able to convert those into what I needed. So x is equal to 1/2 u plus v, and y is equal to 1/2 u minus v. All right. Now I'm ready to try and transform that region. So I want that to be transformed into some region over here, uv. And when I look at this, I've got to figure out what these equations are. So that little line segment right there, that's the equation x equals 0. And notice that my y values are between -1 and -2. So if I come over here and I write down x is 0, that gives me that 1/2 u plus v equals 0. That's this first equation. And then that means u plus v equals 0 if I multiply both sides by 2. So u must equal -v. Or you could say v must equal -u. I think I'll use this one instead. That looks a lot like y equals -x. So that's just a line with a slope -1. But it goes like this. This is v equals -u. Then I'm going to take this one because it's easy. Remember, this was x, this was y. This is y is 0. So if I write down y is 0, we use this equation, which changes that to a minus, changes that to a minus, changes that to a plus and a plus. So you get basically v is u, which would look like this, the diagonal, v is u. And now let's look at